Chapter 6.1, Part 2, Differential Equations. A differential equation is an equation involving a derivative. The order of a differential equation is the order of the highest derivative involved in the equation. So a first order differential equation means that your highest derivative is the first derivative. Your second order differential equation means that your highest derivative is your second derivative in the equation. So, to find general solutions for differential equations. When we're solving differential equations, it is very important that we are splitting the dy and the dx. So we want the dy on the left side with all and every y term, and the dx on the right side with all and every x term. So in order to split these two, I'm going to multiply both sides by dx. So the dx will cancel over here, and we'll be left with dy, and that's going to be equal to secant squared x plus 2x plus 5 times dx. So this right side now looks very similar to the antiderivative integration, so we're going to actually, to solve, integrate both sides. So if you look at the left, that is the integral of 1 dy. So if that was the integral of 1 dx, we know when we take the antiderivative of 1, that's just x if we're looking at dx. But in terms of this, we're looking at dy. So this is just going to equal y. Normally we would put a plus c, but because we're going to integrate both sides would have a plus c or a constant. So we can just put the constant that would be on the left and combine it with the constant on the right so that we're just dealing with one constant. So this is going to be, when we integrate this, the antiderivative of secant squared x is tangent. The antiderivative of 2x is x squared. The antiderivative of 5 is 5x. And then we have a constant. Okay, so we're assuming that the constant from the left has been combined with the constant on the right, and we're just dealing with just one overall constant. Okay, so this is how we solve differential equations. We want to split the dy dx so that the numerator stays on the left, the denominator is multiplied over to the right, and every term with that same variable is on that side. So unfortunately we do not have an example where we have a y term, but we will practice some problems where there's a y term in our equation and we have to split the y term so that it's over to the left and the x terms are all over to the right. So let's do a few more examples together. So for number 2, again we're going to multiply both sides by dx. We're actually also going to rewrite this term, because if we try to integrate x to the negative 1, we'll get x to the 0, which we cannot have. So we're actually going to rewrite this term as 1 over x. So we'll have dy equals, and we're going to rewrite this term so that it is easier to integrate as 5x to the negative 2. So we have dy equals 5x to the negative 2 plus 4 times 1 over x dx. Alright, and now we're going to integrate both sides. This integrates into y equals, and then the antiderivative of 5x to the negative 2, add 1 to my exponent, so negative 1, divide my coefficient by my new exponent, so negative 5, plus, bring out the coefficient, so we have 4, and the antiderivative of 1 over x is ln x, and then plus c. If we wanted to rewrite this so that we don't have any negative exponents, we have y equals negative 5 over x plus 4 ln x plus c. Alright. So now for this next one, we're going to rewrite this denominator so that it is easier to integrate. So we'll rewrite this as x to the negative 1/3 and we're going to multiply both sides by dx. So we have dy equals 6 x to the negative 1/3 dx. And we'll integrate both sides. So we have y equals, add 1 to my exponent, so x to the 2/3. Divide my coefficient by my new exponent. 6 divided by 2/3 is 9. And then plus c. And then the last problem on this page, we have e to the x divided by 3. So again, we're going to multiply both sides by dx. So we have dy is equal to e to the x divided by 3 dx. And we're going to integrate both of those sides. So we have y equals, the antiderivative of e to the anything is e to whatever that anything was. And we're going to plus c, but we want to check to make sure that when we find the derivative of e to the x divided by 3, we get the same thing back. If not, we want to make sure that we're taking that into account. So I'm going to check over here in the corner what the derivative of e to the x over 3 is, and that's going to give me, this is a baby mama situation, so it's going to give me e to the x over 3 times the derivative of x over 3, which is 1/3. So because the derivative of this does not bring me back to my original antiderivative, we want to take into account that 1/3. So in order to get rid of the 1/3, we have to multiply this by 3. So now when we find the derivative of this, we're going to multiply that 1/3 times 3 and it'll cancel itself out. So this is our solution, 3e to the x divided by 3 plus c. Alright, 2 more problems and then we'll move on to the next type of problem. So number 5, dy dx equals 2 cosecant x cotangent x. So again, multiply by dx. So we have dy equals 2 cosecant x cotangent x times dx. We're going to integrate that. So we have y equals, that coefficient can come out, so we have 2. And then cosecant x cotangent x, the antiderivative of that, we know the antiderivative of negative cosecant x cotangent x is cosecant. So since this isn't negative, the antiderivative must be negative cosecant x plus c. And if we simplify this, we'll have y equals negative 2 cosecant x plus c. Right. For number 6, we have dx and we have dy equals sine 2x dx. And when we integrate that, we have y equals the antiderivative of sine is negative cosine. And I just want to, on the side, make sure that when I take the derivative of negative cosine 2x, I actually do get sine 2x. So let's check. So d dx of negative cosine 2x. That's a baby mama situation. So the derivative of negative cosine is sine. And the derivative of 2x is 2. So to take into account and to cancel out the 2, I'm going to have to multiply this by 1/2 and add c. So if I were to rewrite this, I get y equals negative 1/2 cosine 2x plus c. Alright, so now we're going to look at some examples that need a lot more rewriting before finding the antiderivative. So for number 1 of these examples, I'm going to rewrite this whole fraction so that I don't have to deal with the radical sign. So this is equal to x plus 1 times x to the negative 1/2. I'm also just going to distribute this x to the negative 1/2 so that I'm just dealing with polynomials here. So I have x to the 1/2 plus x to the negative 1/2. And that is a lot nicer to take the antiderivative for because we know a rule to help us do that. So I'm going to multiply both sides by dx. So I have dy is equal to x to the 1/2 plus x to the negative 1/2 dx. And when I integrate that, I get y equals, add 1 to my exponent, so x to the 3/2, divide my coefficient by my new exponent, so 2/3, plus add 1 to my exponent, so 1/2, and then divide my coefficient by my new exponent, so 2 plus c. So by rewriting this expression, I was able to find the antiderivative a lot simpler. We're actually going to skip over number 2 and jump right into number 3. So here, I can also rewrite this x squared plus 1 times x squared plus 1. And when I multiply those out, I get x to the 4th plus 2x squared plus 1. And finding the antiderivative for that is a lot simpler than this piece up front. So multiply by dx. So dy equals x to the 4th plus 2x squared plus 1 dx. And if I integrate that, I get y equals x to the 5th, 1/5, plus x cubed, 2/3, plus x plus c. Problem number 4, we're going to also rewrite this by splitting the fraction. So we have 5x cubed over x squared plus 3x over x squared plus 1 over x squared. And by doing that, we can now cancel some things out. So we have 3 x's on the top, 2 on the bottom. That can cancel out, and that just gives us 5x. 1x on the top, 2 x's on the bottom. That'll cancel, and it will give us 3 over x. And then this last one stays as 1 over x squared. And I can rewrite two of these. So 3 over x can be rewritten as 3 times 1 over x. And 1 over x squared can be rewritten as x to the negative 2. So what I'm really doing is dy dx of equals 5x plus 3 times 1 over x plus x to the negative 2. So I'm multiplying by dx. I get dy equals 5x plus 3 times 1 over x plus x to the negative 2 dx. And when I integrate that, I get y equals x squared, 5 divided by 2, plus 3, the antiderivative of 1 over x is ln x, plus x to the negative 1, so my final answer is y equals 5x squared over 2 plus 3 ln x minus 1 over x. And we're also going to skip number 5, just based on time. Alright, so now we're going to do the same thing, but now we want to satisfy an initial condition. So if a derivative of a function is given and the value of the function at a particular point is given, then the function can be determined. So we're going to solve the differential equation, but we're also going to substitute in the initial condition to find our c value. Sorry, this problem has a plus c at the end. So for this first one, we're going to go through the same process, right? Multiply by dx. So we have dy is equal to 3x squared minus 2x plus 1 dx. And then we'll integrate. So we get y equals x cubed minus x squared plus x plus c. And our initial condition states that f of 1 is equal to 2. So when I substitute the value of 1 for x, I should get a value of 2. So I'm going to substitute 1 into my equation. So 1 cubed minus 1 squared plus 1 plus c, and I want that to equal 2. So 1 minus 1 plus 1 is equal to 1. So 1 is equal to c. So our final equation is y equals x cubed minus x squared plus x plus 1. And that is our particular solution to this differential equation. Okay. For the sake of time, and I don't want this video to be too long, I'm going to save problem 2 and 4 for class, and we're going to work on problem number 3. So for problem number 3, we're told that a particle moves along the x-axis at a velocity of v of t equals 1 over square root of t for t greater than 0. At time t equals 1, its position is x equals 4. Find the acceleration and position functions for the particle. So we know v of t equals this. We're going to actually rewrite it so that if we need to find the antiderivative, we can find it a lot quicker. So we're going to rewrite v of t. 1 over square root of t is just t to the negative 1/2. And we want to find the acceleration and the position. So acceleration means find the derivative of v, and position means find the antiderivative of v. So we're going to start by first finding the acceleration. So we know acceleration is a of t, and that's the same as finding the derivative of the velocity. So to find the derivative, bring down the exponent, so negative 1/2 t, and add 1 to my exponent. Subtract 1 to my exponent, so t to the negative 3/2. So that's my acceleration equation. Quick and simple derivative problem. Now to find my position is x of t. Okay, and that means going backwards from velocity. So we're going to take the antiderivative of v of t dt. So we want the antiderivative of t to the negative 1/2 dt. So we'll add 1 to my exponent, so t to the 1/2, and then divide my coefficient by my new exponent, so I'll get 2 plus c. And now this problem told me that at t equals 1, the position was 4. So when I plug in 1 for t, I want my answer to equal 4. So 4 is going to equal 1 to the 1/2, the square root of 1, which is 1. So 2 times 1 is 2, plus c. So c is equal to 2. So my final answer for position, x of t equals 2t to the 1/2 plus